Welcome back guys to the ICND1 video series, and in this video we'll be looking at what routers are, what switches are, and how they fit into our networks. So the first bullet point really sums up what a switch does. A switch allows us to connect our devices to a local area network. Now in the previous video I talked about how local area networks are made up of devices that reside in the same local area and able to communicate and connect with each other. The way that they can actually connect to the network and connect to each other is through a switch. So if you look at the switch over here, the switch essentially has multiple ports, allowing multiple devices to connect to one another. All the devices that connect to this switch will be part of the same local area network, the same network, and they will be able to communicate with one another. The switch itself acts as an access point into our network. A switch, it's essentially the access device which gives us access, allows us into our network. So with LANs, maybe we have a LAN that spans multiple buildings. The devices that connect into our LAN, they'll connect into our LAN via a switch. So what will normally happen is that we'll have devices on multiple floors, and these devices will normally have cabling running into what we call wall jacks. Those wall jacks will have cabling running to the roof, and those wall jacks will actually terminate at a switch. So all these devices will connect to this switch, and so devices that connect to this switch will be able to communicate with one another. Now let's say that we want these guys in this building to also be part of our local area network. Well, what we can actually do, we can put a switch in this building and actually run a switch from the building over here over to this building, so that now devices that connect off this switch are able to communicate with devices in this building. They're able to send data, send file resources, share resources, because they're all connected to the same network. This is known as daisy chaining switches together, and it allows us to have more ports available, which allows us to connect more devices to our network. Now the cable which connects our device to a port on the switch is called an Ethernet cable. Switches themselves come in 8, 24 or 48 port variants, and that just defines how many ports are available on that switch and how many devices that we can have at one time connecting to that switch. If you want to add more devices and we're running out of ports, we just add in another switch, like in this example, and connect devices to that new switch. The switch itself is a third generation device. It's the successor to the hub and the bridge. The hub was a layer 1 device, which was a very basic device, and all it did was just receive electrical signals and send electrical signals. So with a hub, if we had multiple devices that connected to that hub, if one of those devices tried to send some data, tried to send some information, and let's say that information was destined to this PC over here, even though that data should only go to this device over here, when the hub receives that packet, that data, it's going to forward that data out every single one of its ports. This was obviously very unsecure, because if we had somebody connected off the hub and that guy had some packet capturing software open, he could capture that traffic, save it for a later time, and then actually analyze that traffic. Devices that are connected to a hub also shared the bandwidth offered by the hub. So if this hub was 100 megabits per second of bandwidth, they would have to share that. And because they'd have to share the bandwidth offered by the hub, it meant that only one device at any given time could send data. So if this guy wanted to send, but this guy was already sending, this guy would have to wait until this guy has finished sending data before he could send. Now if both devices try to send at the same time, their data, their packets would collide, get corrupted, get scrambled, and both devices would have to wait a certain amount of time before they can try to resend again. This is what we call a single collision domain. So by single collision domain, these devices all connect to the same network segment. This is a shared network segment, and only one device can send at a time. So if two devices try to send, the data will collide, and this will cause the data to become corrupted, and they'll have to resend. So a hub represents a single collision domain, meaning only one person can send at a single time. Now if you added another hub over here, both hubs would be part of the same collision domain. So devices off here would have to wait until either this guy has finished sending or this guy has finished sending before they could try to send. devices of each hub could not send simultaneously. So after the hub came the bridge, and the bridge was an improvement over the hub, but it didn't necessarily replace the hub. It was used in conjunction with the hub. So in the previous slide I mentioned how a single hub represents its own collision domain, which means that when multiple devices try to send that connect to the hub, their data will collide and it will be dropped. This is why only one device can send at a single time. By connecting a bridge to our hub, we're able to separate our network into individual collision domains, which means that we can have more than one device sending at a single time. So if we had a hub of here and we had devices connected off the hub, that means that devices from this section and devices from this section can send at the same time. If this guy over here wants to send data, he will still have to wait for this guy to finish sending before he can send. Because again, they're all connected to the same collision domain, they're all connected to the same network segment. But by introducing a bridge, we can separate our network into multiple network segments and collision domains, making a more effective use of our bandwidth. So devices here would have to share the bandwidth of it here, and devices here would have to share the bandwidth of it here. And by bandwidth, I mean this the speed at which data can be sent and received. So essentially, the higher the bandwidth, the faster you can send and receive data. Switches came after the bridge, and they combined the functions of a bridge and a hub kind of together. So with a switch had a multiple ports like a hub, and each port was its own collision domain. Each port was its own individual network segment, which meant that we could have multiple devices connected to this switch, and they could all send and receive data at the same time. They would also all receive dedicated bandwidth. So by having dedicated bandwidth, it means that they wouldn't have to share the bandwidth offered, and they wouldn't have to share who can send. So if this was a 100 megabit per second switch, this guy would get a full 100 megabits per second, and so would this guy, and this guy, and this guy over here. Switches were also very intelligent devices in that they can actually learn who's connected of each port. So in this case, if we had PCA over here and we had PCB over here, and just for grins, let's add PCC over here. The switch will actually know that PCA resides of this port, PCB lives of this port, and PCC lives of this port. So now if PCA wants to communicate with PCB, when the data enters the switch will know that to reach PCB, all he has to do is send the data back at this port, because that's where PCB lives. It can leave sending data out this port and this port because it knows that PCB doesn't live off these ports. PCB is reachable from this port, making more effective use of our bandwidth, which wastes the unnecessary traffic which is on our networks. Now, a switch represents a broadcast domain. So if I draw my switch again, I shouldn't have actually declared that, but if I draw my switch again, a broadcast packet is a packet sent by one device which is delivered to all other devices on that local area network, on that network. So in this case, if PCA were to send a broadcast message, that message would be sent to PCB and also to PCC and PCD. And if we had a connection to another switch, that broadcast will be sent to this switch and be forwarded on to all the other devices of this switch. So by adding switches together, we can increase our broadcast domain. So obviously, the more switches we add together, the more computers and devices that we add to our network, the larger our broadcast domain will be. Now, the problem with broadcasts is that because broadcasts are sent to every device, they have to be processed by every device, which means if we have too much broadcast traffic on our network, it can actually be a negative and slow our network down. The reason why we have broadcast traffic is so that when a device wants to reach another device, and a switch, or when it doesn't know the addresses that it needs to use to reach those devices, it can send a broadcast message so that it ensures that data gets there. MAC addresses themselves are called media access control. They're 12-digit hexadecimal 48-bit addresses, and those are the addresses given to a device when it's first manufactured. Ethernet is a protocol which defines a set of rules and standards for layer 2 communication, so for communication between devices on the same network. And Ethernet says that for two devices to be able to communicate locally, for two local devices to be able to communicate, they have to use their MAC addresses. That's why a switch learns MAC addresses. It's only concerned with local communication between devices on the same network, whether that be a network which spans a single floor or a network that spans multiple buildings. These devices in these buildings will all communicate with each other by using their MAC addresses. So, like I said before, if our broadcast domain gets too big, that can cause a problem. The way that we can segment and split up our broadcast domain and essentially stop and limit the size of our broadcast domain is through routers. Routers connect our networks together. So routers is the device used in wide area networks to actually connect all of the local area networks together. So essentially, if we have a network over here, there'll be a router at the edge of a network which has a connection, let's say, to another network. And what that means is that devices in this network will be able to communicate with devices in this network through their router. Also means that the router will also stop broadcast from leaving this network. So what happens? A device over here in this network sends a broadcast. The router will actually receive that broadcast, but the router will by no means forward the broadcast onto other networks. So it won't forward that broadcast out any of the other interfaces, because each interface represents its own broadcast domain. Each interface connects to a different network. Routers themselves are software based, which means any forwarding decisions are made in software. There's also a slight delay because the hardware has to communicate with the software before a decision is made, and those differ from switches. Switches are hardware based. Switches have what we call specialized chips built in, which are used to perform specific functions, and because this is all done at the hardware level, there's no delay between any choices which are made, because everything is performed by hardware. There's a delay with the router because the hardware of a router has to talk to the software first before anything can happen. With a switch, all decisions are made on hardware, made with these ASIC chips, which makes them really, really fast. Routers, to be able to connect our networks together, they have to learn routes on how to reach the different networks. So if we had a small enterprise network, unlike in the example in the previous video, we have a network in Hong Kong, we have a network in London, and we have a network in Madrid. This is what we call a WAN. It connects our networks together. The routers at the edge of these respective LANs, and the routers that connect us to the WAN, they'd have to know routes on how to reach our different networks. So as you can see, the router in London doesn't have a direct connection to the router in Madrid. So he has to know that he has to find out, there has to be some way for him to know that to reach devices in Madrid, he has to go through the router in Hong Kong to reach devices in Madrid. There's two ways that we can do this. We can either tell the router ourselves, or we can configure dynamic routing protocols so that the router in Hong Kong lets the router in London know that to reach devices in Madrid, you have to use me. Routers are also feature rich. They have a lot more features than switches, such as NAT, DHCP, they can act at the web server. And this is the main reason why they're software based. It's easier to add more features to software than it is to have to remanufacture hardware for those specific features. So in this video, we've talked about what routers and switches are. We've seen how they fit into our network. Switches fit into our local area network, allow for local communication. So in the previous video, I was talking about how local area networks are devices in a close proximity of each other. They're able to communicate. They're able to communicate through a switch, so they all connect to a switch, which allows them to communicate with each other. And with routers fit into the wide area network picture, in which wide area networks connect our local area network to other networks, connect all of our networks together, and that's done through a device called a router. A router connects all of our networks together. It limits broadcast, stops broadcast from lapping over into another network. It's software based, has more features than a switch. As you can see, these are the two main building blocks. So without switches and routers, we can't have a network. I hope this has been informative for you, and I'd like to thank you for viewing.